Okay, I wanted to make a video on studying period synchronization, like a woman's menstruation cycle. Do they synchronize when you have two women living in the same house? So I said, okay, let me write a Monte Carlo simulation. There's Monte Carlo. This is Osiris. He helped me write the simulation. So what we're going to do is we're going to look at variability in a woman's, the length of a woman's menstruation cycle. So the average is about 28 days, but there's some variation around that. And so I'm going to write a Monte Carlo program that each woman independently has slight variation in the length of her menstruation cycle, and I'll have two or more women, and we'll just evolve that in time. Evolve this, sometimes it's a little bit longer, sometimes it's a little bit shorter. I'll sample that from the actual tabulated distribution of a woman's menstruation period, and we'll see when we'll look at when the two women are in phase and out of phase of having their period. And so the way I'm going to do it is completely uncorrelated. The sampling is completely uncorrelated, and we'll look at how the results, how you can interpret some of the results as, you know, oh my God, our periods are synchronizing, especially if you allow for. Uh-oh, somebody's hungry. My cameraman is hungry. We're going to have to pause the video. Okay. We are going to look at the variation in the length of a woman's menstruation cycle. So I found this data on the internet. The average menstruation length is 28 days. So that occurs most frequently, but it doesn't have to be 28 days. It could be a little shorter, 27 or 29 days, you know, and it could be as much as 35 days with a very low probability, or as few as 20 days with a very low probability. So it follows some distribution. So I put this distribution into my Python program, and of course we are going to use the Monte Carlo method, which means we're going to randomly select the length of a woman's period from this distribution. The other thing we want to look at is how long the woman is bleeding for. Well, we've got some action going on there between the animals. Okay, so there's a very small probability that it's 3 days. It's more likely to be 4, 5, 6 days, 7 days, a very small probability of 8 days. So again, we're going to draw from this random distribution for how long the woman's going to be bleeding. So that's what I'm going to do. I'm going to simulate this for years and years and years, two independent women that have no correlation at all with each other, and we're just going to look to see do their periods fall in phase or not, just due to this random variation of how long their period is and how long they're bleeding for. And I'm going to start them off perfectly synchronized. Day one, they're both on their period and bleeding. And then I just roll a random number. How long is the next period? How long is the next period? How long is the next period? And let's just watch what happens. And so they're sampled completely independently. So here's the result of the simulation. They start off synchronized. They're both, they just started their period and they're bleeding. So blue is woman 0 and orange is woman 1. And here's the day along this axis. So 1 means bleeding, 0 means not bleeding. And every time I sample the length of the period according to that distribution and the length of the bleeding according to that distribution. So it looks like right away they fall out of phase, then they're back in phase. By in phase, that's when their bleeding is synchronized. So it appears to be synchronized, then they get somewhat out of synchronized. So this is for about 1 year's worth of data. So now we can scroll this over. For the second year of data, pretty much synchronized here. They're a little bit out of phase. And this is just all due to randomness. So these computer models does not know anything about roommates or hormones or anything else, just drawing random numbers from a distribution. So now it looks like they get out of phase due to this randomness. Then they're in phase, out of phase. So we're just looking at the data. So this is what, about 5 years worth of data. Now out of phase, in phase. So we're seeing that we can oh, now they're out of phase. But this is only looking for bleeding on exactly the same day. But frequently, what happens is you might say, "Oh, I just had my period," so I'm gonna add a modification to the program that allows for a little bit of overlap in when they had the period. So now I'm running the same simulation, but I have this synchronization term in here, which shows if the two are bleeding within 6 days of each other. So we see a lot of synchronization because it's putting a window, a pad around each person's, a pad, so to speak, around each person's period of 6 days. So they're more likely to report synchronization, which is perhaps how human beings behave. They say, I'm on my period. Oh, I was just on my period. Like these two, they're actually disjoint. If you can see, the green and orange bars are disjoint, but because they're within 6 days of each other, they're counted as a match. Same thing here. They're disjoint, but counted as a match. These two are far enough apart that they're not counted as synchronized, so we don't have the match. So we can just kind of scroll through the years, and I guess these are far enough apart that they're not matching. But we see, just due to randomness alone, we see this notion of being in phase or not. Now let me try 4 women. Okay, so now we have woman 0, 1, 2, 3, and 4. So we have 4 different women sampled completely independently, and then we're looking at this synchronization thing. Are any 2 of them having a period together? And because we have more pairs, they're more likely to be synchronized. So this indicator is saying how many of them are synchronized. So, I mean, if any 2 are nearly almost always synchronized. Let me put it on this pan thing, and we can pan. There's 1 year. So the point I'm trying to make is that through random variation in the length of your period alone, you have this perceived synchronization that you're either going to find some friend who you're having a period with or close enough to when you last had your period. Here's another way to think about it in terms of average length of period. Say the average length of a period is 28 days, and say the average time you're bleeding is around 7 days. And now we have 2 women, and we want to know, do their periods coincide during any of the days? So one woman is bleeding 25% of the time, the other woman is bleeding 25% of the time. Do those intervals overlap at all? Well, about 50% of the time, they'll overlap by at least 1 day. So this kind of perceived synchronization is kind of inevitable. And then as you throw in a 3rd woman, then that's going to, cover 75% of the time that any 2 overlap. Throw in a 4th woman, and 100% of the time, any 2 will overlap. And then you throw in, I just had my period. You add extra padding around that, and we can explain. And the other thing is, people are more likely to notice when things match, and they ignore all the times they don't match. So using the Monte Carlo method, we've demonstrated that just through random chance alone, we can see how these periods appear to coincide, especially when you allow yourself wiggle room of saying, I just had my period a couple days ago. You're increasing the length of the interval to overlap with another person. So I thought that was a nice application of the Monte Carlo method, and I thought it was a nice explanation of explaining you can observe period synchronization even though there is no actual synchronization. It's just looking at the data, things kind of fall in and out of phase, and it's just sort of a natural consequence of random variability of the length of your menstruation cycle. And thank you very much.